Welcome back, my dear students. So in our previous class, we have learned the expression for potential, that is electric potential. Then we have learned an expression for electric potential due to a point charge, electric potential due to a dipole, correct? And we have learned some of the difference between the electric potential and electric field, electric potential due to a point charge and electric potential due to a dipole. In today's class, we will learn about the equipotential surface, that is equipotential surface. From the word equipotential, surface or equipotential means a surface where potential at all the points are same, equal. So what I can say, equipotential surface is a surface where potential is same at all the points. Okay, and it is a property. For a charged conductor, potential inside the charged conductor is always same at all the points. So if the potential is same at all the points, wherever you check, here what is the potential? V. Here V. Here V. Okay. For a charged conductor, potential inside the charged conductor is same or at all the points. So if I want to move a charge from one point to another point in an equipotential surface, what is the work done? How much work is done to move a charge from one point to another point in an equipotential surface? What is W? W is nothing but work done. We can say work done is nothing but change in potential, correct? So change in potential is what? What the potential present over here is equal to the potential present at this point also. So therefore, I can say work done is equal to change in the potential is nothing but equal to 0 in an equipotential surface, because potential at this point and this point are one and the same. So if you subtract, the answer will be 0. Understood? So equipotential surface is a surface in which the potentials are same at all the points. And in an equipotential surface, if you want to move a charge from one point to another point, work done is equal to 0. Okay, always work done is equal to 0. Then next, we have to learn some of the properties of this equipotential charges or equipotential surface. Sorry, not charges, equipotential surface. So I can say all the points of equipotential surfaces are same. All the points on the equipotential surface, at all the points on the equipotential surface are having same potentials. Second point, the work done in moving a charge from one point to another point in an equipotential surface is 0. Electric field is always normal to the equipotential surface. When we draw the electric field, it is normal to the surface. Always electric field is drawn normal to the equipotential surface. Next, what the next? Two equipotential surfaces never cross each other. Two equipotential surfaces never cross each other. Then component along the electric field along the equipotential surface is 0. Electric field along the equipotential surface. Electric field is always normal to the equipotential surface, and electric field along the equipotential surface is 0. Then, so these are the few points. So first point, what I can say, on the equipotential surface, every point on the equipotential surface are having same potential. Then work done in moving the charge from one point to another point in an equipotential surface is 0. Then third point, no two equipotential surface cross each other. If they cross, then the direction changes. So it is not possible. So third one, no two equipotential surface never cross each other. Fourth one, electric field lines are always normal drawn to the equipotential surface. So these are the few properties of the equipotential surface, important for 2 marks. Suppose if we want to draw a equipotential surface for 1 mark, if the question is asked, draw equipotential surface diagram, then for a positive charge, equally distributed, like this. For a negative charge, again like this, equally distributed. Then for a dipole, how can we draw equipotential surface? 2 poles are there, plus and minus, okay, 2 poles are there. They are unlike poles, so there will be attractive force. So therefore, this side little bit more compared to the other end, tries to move this side, like this. Like this. This is nothing but between the equipotential surface around a dipole. Then equipotential surface around 2 identical positive charges. If we keep 2 positive charges itself, it will repel. So therefore, which side it has to move? Sorry. Like this. So it will try to move away. Understood? Once again we will draw it for a positive, see, plus, plus. This was attracting nearby, so this side nearer it is. Now it is repelling, so this side it should be smaller radius compared to that side. So like this. And for the other charge, like this. It will be here the distance is more compared to this side. Here distance is more compared to this side. This is how we draw equipotential diagrams around a 2 positive charges and around the dipole. Next, the concept what we are moving for is one simple derivation. One simple derivation, that is relation between electric field and electric potential. Relation between electric field and potential. In our previous class, we have learned the difference between electric field and electric potential. In today's class, we will learn what is the relation between electric field and potential. So for that, what we have to do initially is, let us consider 2 conductors. Okay, one conductor, another one conductor we will consider. Okay, we have considered 2 conductors. They are separate, just like this it is. They are separated by the distance delta L. Okay, 2 conductors are there. They are separated by the distance, just like this. There are two conductors. They are separated by the distance delta L. Let this one be the A, first one. Let this be B. Let A be having the potential V and BB having the potential V plus delta V. Okay. Before moving to this concept, I will help you with some small example for understanding this concept. You know, if we have two water tanks, let one water tank filled, another water tank is partially filled. This is fully filled, this is partially filled. If I make a connection from one water tank to another tank, both are at same level, okay, water will start moving from one water tank to another water tank. From where to where? From a water tank which is filled to the water tank which is partially filled. Till what? It will flow from higher level to lower level until both the tanks will have same water level. In the same way, always the charges moves from a region of higher potential to a region of lower potential. Always the charges move from a region of higher potential to a region of lower potential. Just like the temperature, if we have two bodies, one is cold body, another one is hot body. Always heat flows from hot body to cold body until the temperature becomes equal, correct? In the same way, the charges flow from higher temperature region to lower temperature region until the potential becomes equal. Once the potential is equal, no charges flow from one conductor to another conductor. Okay. Now, let the charge move from the B to A. Let us make the charge to move from B to A. Therefore, potential difference is VA minus VB. This potential difference is nothing but work done, correct? Potential difference is nothing but work done according to our first. In the beginning of this chapter, we have seen that work done is nothing but change in potential. Okay, so W is equal to V, that is change in potential, that is VA minus VB. VA is nothing but V minus, so I'll write it directly. Work done is equal to VA minus VB, that is minus V plus delta V, because this one's VA is V, VB is V plus delta V. Then we'll get here V minus delta V, that is equal to work done is equal to delta V, because V and V gets cancelled. So work done is equal to delta V. What we have considered? We have considered two conductors, A and B. They are separated by the distance delta L. Let A be having the potential V, B be having the potential V plus delta V. So we want, let the charge move from B to A, because B is having higher potential. Let the charge move from higher potential to lower potential. Whenever there is a charge, there is electric field drawn normal to this equipotential surface. So in this equipotential, we have considered what? Equipotential surface. So whatever this surface, that is A surface is having, it is having V. Wherever you check, there the potential will be V. For this B, wherever you check, the potential will be V plus delta V. So electric field is drawn normal to this potential surface. Okay. So W is equal to delta V we get. Next, we also know that W is equal to force into displacement. Correct? The force is nothing but electric field into charge into displacement is here delta L. Here we are moving the unit positive charge. So therefore Q is equal to 1 electric field into delta L. Correct? Sorry, here minus sign is left out. Okay. W is equal to minus delta V. Here W is equal to E into delta L. So by equating 1 and 2, we get, okay, equate, shall I write it over here? Yes. Equate 1 and 2, because both are work done. So I can write E into delta L is equal to minus delta V, or electric field is equal to minus delta V by delta L. This is the relation between the electric field and potential. So what we have done, we have considered two equipotential surfaces A and B. Let V be the potential of A and V plus delta V be the potential of B. E be the electric field drawn normal to the surface. Now, let us make the unit positive charge to move from B to A. So, the work done is nothing but change in the potential. That is VA minus VB. VA is V, VB is V plus delta V. Open the brackets, we get V minus delta V. VV gets cancelled, minus delta V will remain. So, work done is nothing. We also know that work done is nothing but force into displacement. Force is nothing but E into Q and displacement is delta L. So Q is nothing but 1 unit positive charge. So W is equal to E into delta L. We can equate equation 1 and 2 because both are work done. Therefore we get E into delta L is equal to minus delta L, or E is equal to minus delta V by delta L. This derivation is very, very, very important for 3 marks. Very, very, very important derivation for 3 marks. What does this negative sign indicates? Negative sign says that electric field is in the direction which the potential decreases steepest. The electric field is in the direction in which potential decreases very, very high. Potential will decrease steepest. Next. The next concept what we are moving for is, we will solve one problem. Then we will move further. One simple and easy problem we'll go for. That is, write down. Charges. This derivation is very, very important for 3 marks. Learn this derivation. Simple and easy derivation. Nothing like difficult and all. Okay. Next. Charges. 20 microcoulomb and minus 30 microcoulomb. And also minus 40 microcoulomb are placed at the corners. A, B and C of square A, B, C, D of side 2 meter. Calculate the work done to move. Calculate the work done to move an electron from center of square to corner D. Center of square to corner D. What is the question? Charges 20 microcoulomb and minus 30 coulomb and also minus 40 microcoulomb are placed at the corners A, B and C of a square ABCD of side 2 meter. Calculate the work done to move an electron from the center of the square to the corner D. Okay, so we have to take one square A, B, C, D, you have to place the three charges, 20 microcoulomb, minus 30 microcoulomb and minus 40 microcoulomb at the three corners of the square of side. How much? 2 meter, 2 meter, 2 meter, 2 meter. Calculate the work done to move electron from the center. Okay, so to draw the center, we'll draw a diagonal. Okay, from the center you have to move to the corner D. You have to move the electron from center to D. What is the work done? How to calculate? Let us use the expression of potential, that is V is equal to 1 by 4 pi epsilon naught Q by R is the expression. If there is a system of charge, then you have to add the charges of all these three separately. So total potential according to superposition principle, I can write total potential due to all these three charges is equal to 1 by 4 pi epsilon naught acting at this point, correct? Acting at this point due to this one, this distance, due to this one, this distance, due to this one, this distance. So 1 by 4 pi epsilon naught. What is the distance value? We don't know. Okay. Q1 by R1 plus 1 by 4 pi epsilon naught Q2 by R2 plus 1 by 4 pi epsilon naught Q3 by R3. But we don't know what is R1, R2, R3. We know only these sides. How to calculate this distance? Just like your previous chapters, problems. How to solve? How to find out this diagonal's value? How to find out? Diagonal. This is by using a Pythagoras theorem. You can find out the distance of this one, AC. How? AC square is equal to AB square plus BC square. Correct? So AC is equal to square root of AB square, that is 2 square plus 2 square is equal to square root of 4 plus 4, that is square root of 8. That is square root of 8 is nothing but 2 root 2, because 4 2s are 8, 2 root 2. AC is equal to 2 root 2, but we want AO. So therefore, I can say AO is equal to, or OA is equal to AC by 2. That is equal to 2 root 2 by 2. So I'll get root 2 is the answer, root 2 meter. So, and also this is, since it is a square, I can say OA is equal to OB is equal to OC equal to OD is equal to root 2 meter. What we have done, we have taken this one as a right angle triangle since it is a square. So use the Pythagoras theorem and you can find out the value of AC. AC is equal to 2 root 2. Then next step, what we can further move for? The next step, can you please help me? Substitute for this formula, that is V is equal to 1 by 4 pi epsilon naught is common. So I'll write 9 into 10 to the power 9. Q1 20 micro divided by OA. R1 is this one. R2, R3. OA is how much? Root 2 plus minus 30, 10 to the power minus 6 by root 2 plus minus 40 into 10 to the power minus 6 by root 2. Next, what is the answer? Can you help me for the answer? What is the answer? Solution please. So total potential at O due to the 3 charges is 9 into 10 to the power 9. That will be 9 into 10 to the power minus 6, minus 6, minus 6. So 3. Okay. By root 2. 20 minus 30 minus 40. What is the answer remaining? Can you give me the answer now? Take a calculator and solve. Minus 3.18 into 10 to the power 5 volt. Minus 3.18 into 10 to the power 5 volt we get. Next, what we have to find, what is the work done in moving the charge, or that is electron, from center to the D. This is the potential at that point, correct? So, how much work done? We know that work done is equal to, how much work should be done? How to calculate? First, we have to calculate the potential due to all charges at D. What is the potential due to all these 3 charges at D? This is the potential at O. Find out the potential at D. The difference at O and D will give you the work done in moving, because we know that work done is nothing but change in potential, that is VO minus VD. So first we got VO now, that is at O due to the 3. Next, to find out potential at D due to the 3 charges. So on this D distance 2 meter, this distance is how much? AC, that is 2 root 2. Then this distance is again 2. Use those 3 distance and calculate value of potential at D. Then subtract, that is nothing but work done. VD is equal to 9 into 10 to the power 9. First one, 20 into 10 to the power minus 6 by 2 plus minus 30 into 10 to the power minus 6 by 2 root 2 plus minus 40 into 10 to the power minus 6 by 2. Calculate VD. You will get one answer. We got the answer as minus 1.855 into 10 to the power 5 volt. Therefore, work done is equal to VO minus VD. So, what is the work done? To move from O to D. So, since it is O to D, we will not take it as O minus D. We have to take it as DO, D to O. See in the previous one, for 2, we are moving from B to A. So, we have taken VA minus VB. Same way here, we have to move from O to D. So, VD minus VO. Substitute and calculate work done. We will get here work done is equal to, change in potential is nothing but 1.325. We'll write change in potential, that time it will be very easy. 1.325 into 10 to the power 5 volt. That is potential. How to calculate how to calculate work done? Is there any relation between work done and potential? Work done and potential, work done is equal to, we know that potential is nothing but work done per unit charge. So, work done is equal to V into Q. That is equal to, V is this delta V. Charge is nothing but electron. Charge of the electron you have to substitute. So 1.325 into 10 to the power 5 into 1.6 into 10 to the power minus 19. What is the answer you get? That is the solution. That is work done. 212.6 into